Well, I will be talking about some problems in higher spin theories, which are of different types. Some I would like to talk a little bit on those that I believe are most important in this theory, as well as on those that are currently under study. So basically my talk will be a mixture of several issues, and the presentation has been changed by recent surprises during the last week, actually, to some extent. So I will comment on the recent papers and claims. The most important part of the story, which is still not very well investigated, very well studied, is what is a possible relation of higher spin gauge theories with string theory. And this is actually a very old subject. Probably the first ideas on this issue, maybe even not the first papers, are due to Gross in the 80s. And also from the higher spin story side, we discussed this with flattened more around the same time. So recently there was some very impressive progress in understanding this relation in the framework of ADS3 due to a number of papers by Matthias, Rajesh, and co-authors. So actually there is some new indications that there must be some relation. So I believe that this is one of the very important and most important problems, and actually I will make some comments on this in the beginning of my talk, at the same time providing a background to what I'm going to talk about. So the next issue is holography. Holography in higher spin theory is due to the pioneer paper by Bo Sandberg, who is here in the audience, I hope. And yes. And actually that was the beginning of the story. And around the same time, Witten also expressed somewhat similar ideas, but the precise conjecture was made by Klebanov and Polyakov on this vector model duality. And then first checks came with the papers by Joan in 7 years after. Still, the problem is not fully clear, because some original Klebanov-Polyakov conjecture is actually, we can say that it has been solved, has been checked, but there was a more general conjecture due to Aroni, Gurari, Jacobi, and also Jombi, Minwala, and other people. That was a conjecture on the relation of Chern-Simons-like theory at the boundary, conformal theories, to the higher spin theories in the bulk. And that has been only partly checked so far, and the full understanding was lacking, and I would say still is lacking. And this is where we hope to get some progress just around these days, this time. I will talk a little bit on this issue in the very end of my talk, but more specifically I will discuss the point that may look be technical. This is the issue: what is local, what is non-local, or better to say what is minimally non-local and what is genuinely non-local in higher spin theory. This is a difficult issue that probably the importance of it was first realized in the paper with Prakushtin, where actually the ADS3 model was proposed. And then more recently there was a discussion of these issues in a number of papers where authors were arriving at somewhat different conclusions. And I will discuss on this, also mentioning the very last paper by Slate and Taron on this issue. So that probably will be the main part of my talk. To begin with, let me start with the simplest conformal field theory in 3 dimensions and explain what higher spin symmetry is, where it comes from here, and also setting up the formalism that I will be systematically using in the rest of my talk. So the simplest system in 3 dimensions is just a free massless scalar, for example, or spinor. And to begin with, let me reformulate this system in a slightly unusual way, which we call sometimes unfolded machinery, which is the first order formulation with respect to all 3-dimensional coordinates. The claim is that this simple equation on the generating function that depends both on x and on these auxiliary spinor variables y alpha, where alpha is a 2+1 dimensional Majorana spinor index, then it is equivalent to the Klein-Gordon or Dirac with zero rest mass. How one can see that? Well, actually, it's not difficult at all to see, because first one observes that all those components in the power series expansion of this function in y that are of order 2 in y or higher, they can be expressed in terms of ddx derivatives of the primary components, which are correspondingly are either y-independent or linear in y for spinors. So y-independent is a scalar, linear part is just a spinor. And in accordance with the spin statistics, well, number of spinorial indices is related to whether or the function is bosonic or fermionic. So the scalar field is given by just this primary of the conformal modulo, which in fact is explicitly realized by this equation. So the meaning of all other components is very simple. These are just descendants associated to the primary scalar field in the module. And that's what makes conformal symmetry manifest. At the same time, immediately answers the question, what are infinite dimensional symmetries that leave this equation invariant? It's actually not that trivial to answer this question in standard formalism. In this formalism, we immediately get an answer in one line, because one should take into account that if we, for example, know at every given point x, for instance, x equals 0, this function as a function of y, we know everything locally. Because knowing the dependence on y, we know ddx, the second derivative, third derivative, all derivatives in x, and this means that locally we know everything about this field. Okay, so this is a locally full description and substitute for the standard Cauchy problem in the system. And now it is fairly clear that the maximal symmetry on the space of solutions is just maximal symmetry acting on the functions of y, which, if we want local symmetries, is a symmetry of differential operators with polynomial coefficients acting on these y variables. That's it. Well, this is a very well-known mathematical object known as a Weil algebra, and as a subalgebra of bilinears built out of these y ddy's, we get immediately as before, which is nothing else as three-dimensional conformal algebra, which is equivalent, of course, to the four-dimensional ADS algebra. So we actually, without any problem, we derived what is a three-dimensional higher-spin algebra. It is a Weil algebra. This is the algebra of symmetries of these equations. Any questions to this? Okay. So let me emphasize again that it is important to use the observation that instead of using space-time coordinates x, one can use systematically dependence on the variables y, which for simplicity I will call twistor variables. They are not quite twistor variables in the standard for mathematicians. I would not call them twistor variables, but they are somehow similar. All right. Now the same way one can describe conserved currents. So in this language, conserved currents are pretty much similarly described by these first-order equations. Now they depend on a doubled number of spinors. There are two spinors here, and here is the equation. The claim is that, number one, this equation is satisfied by these bilinears of the scalar field. It's just very simple to check using the chain rule, acting by ddx on every of this field. And that actually gives us the full list of conformal modules associated with conserved currents in 2+1 dimension. This construction is somewhat similar to the construction that Antal Ivisti is using in terms of bilinear fields, but the difference is that here these are bilinear objects, but they're bilinear in these y and u variables. So in twistors, if you like, not an x variable. So this current is given at the same x. It actually contains all conserved currents that can be built in terms of a scalar and spinor at the same time. And the primaries can be easily deduced corresponding to all primaries for conserved currents in 2+1 dimension. Well, one can easily check that they indeed obey these conservation conditions as a consequence of the unfolded equation here. Okay. Uh, uh, let me explain where I'm going to go now. So we have found what the symmetry algebra of free fields is. This is a higher spin algebra. Where we want to go is to find a much larger algebra that would have a chance to be identified with a stringy higher spin algebra rich enough to describe the full-fledged string theory. So this is the next step. I will actually derive in 2 slides what one conjecture that I believe has a good chance to work. And again, I will use the same trick. I will use this y dependence. And now the game is that why don't we quantize our fields? And why don't we find the operator algebra of conserved currents at the boundary just in one shot? Turns out that it is not difficult to do using this trick with going to the twistor space. Well, let me make a comment that, of course, we are talking about free fields, so it's not a big deal naively to compute operator algebra for free fields by just applying the standard machinery. However, to get a unified formula for all spins, it's much more tricky to get the closed formula for all this operator algebra and to understand its algebraic meaning. So this is what we are going to do now. Okay, so if we quantize fields that we are using, scalar and spinor, in a standard fashion following textbooks, but now keeping y dependence arbitrary, we can deduce the commutation relations like this, which of course reproduce at 0 values of y, reproduce usual gain functions. It's not a big deal, 2-point function. However, the trick is that if you now do something that normally is not allowed in field theory, I'm going to consider these commutation relations at the same x. It's not x prime, it will be the same x. But I will keep y's different. And this is possible and has perfect sense. And this is something that people not necessarily can immediately appreciate. The point is that the commutation relations in this language becomes just a delta function in y's. That's it. This is the simplest possible 2-point function, I think, that one can imagine. These are commutation relations for 2 quantum fields at the same x, given that y and y bar are different. These commutation relations would not have sense in the corresponding 4-dimensional construction for fields of given spin, because fields of given spin carry particular power in degree in y and y bar, and this delta function, I mean, it will be delta, some derivative of delta function at y equals 0, which makes no sense. But they make very clear sense when all tower of higher spin fields is involved in 4 dimensions. Here we, so far considering 3-dimensional case where just 2 fields are around. All right, so the idea is, why don't we compute the full operator algebra at the same x, at the same point of space-time, but at different y's, see what will happen, and then we can reconstruct the x dependence by just using, oh boy, we were checking, I mean. So the main formula is not visible here for some reason. Well, let me just spell what it was supposed to be. So here is the formula that reconstructs x dependence in terms of y variables. So we're checking actually that I had this problem in the previous talk given here, and we checked that it does not show up, but the check was not completed probably. Let me try. Yeah, it's a little bit better indeed. Oops. Okay, so here is a formula that reconstructs y-x dependence in terms of y primed, x primed, here using only integration over y's. This is important. There is no integration over x's, even though the x and the x primed are different. The idea is that one can actually reconstruct the dependence integrating over any 2-dimensional surface in the x, y space. So that is the formula how it works. So if we will know the dependence on y variable completely, we will be able to reconstruct the whole story. Okay. Good. And now I'm nearly ready to answer the question, what is the operator algebra for all three currents in 2 + 1 dimensions? Well, these are further operator products of this J build out of a couple of C. I can add vector model indices if I like. I just, they don't contribute much except to the central charge term. This n is just the number of fields. And it is useful to parameterize all this infinite collection of fields in terms of generating function g, which is a kind of a test function that is used to construct all indices. Then one can compute j2 to j2, which is very simple, finding the following important result, that of course there is a regular term, but also there are singular terms containing j and j primed commutator with respect to, it's not quite star product, it is what's called convolution product, which is a half Fourier transform from the star product in the normal field. But I will use the same name, it's practically the same story. And there is a central term that accounts how many fields are there, built in terms of the trace on this algebra, which is just integral. Okay, so one can go on, one can compute, actually get explicit formula for all these higher-spin higher operators in the game, and the full list of operators is given just by various m here. I'm not giving here the formula. It actually was obtained in the paper with Gelfond about 4 years ago. But I will just spell what is the final result. The final result, because of the simple relation that commutator of two currents is a current of a commutator that follows from here, implies immediately that the resulting algebra is nothing else as universal enveloping algebra of the higher spin algebra. So we started with infinite dimensional algebra, which was higher spin algebra, Weil algebra. And if we consider the full list of currents, we will get something far larger. We will get universal enveloping algebra of the higher spin algebra. This is a huge algebra containing a lot more states than original higher spin theory did. Okay. Now let me discuss a little bit this issue, as well as the issue how good is life in the Y space. So I believe that the life in Y space is just beautiful. It's in many respects much better than an X space, but for some historical reasons we not necessarily can appreciate this immediately. So actually all kind of issues, including what is local, what is non-local in space-time sense, and actually what is unitary, what is non-unitary in space-time sense, can be analyzed in terms of Y variables. In particular, this language of first-order unfolded formulation is pretty much convenient for analyzing unitarity in theories with infinite number of space-time derivatives, in particular time derivatives, because it actually operates with immediately with the modules which are complex equivalent to the modulus of single particle states. So we can control whether our equations keep the norm finite or not in this language with no reference to Hamiltonian formalism direct. So this formalism is very convenient in this case. So it allows us to reproduce explicitly all correlators in the three-dimensional models. Actually, Zhenya Skvortsov mentioned in his yesterday talk that it was computed by him and Didenko from the ADS-CFT side. It was almost correct, but I mean the comment is that it was computed by the higher spin symmetry principle, which means that up to a constant for every particular correlator in particular, here all constants are fixed uniquely, and group theoretically they are fixed by this much higher symmetry, by this multi-particle symmetry. That's what fixes all relative coefficients for these correlators. So the number of states gets much, much richer. It's infinity to the power infinity, if you like. And suddenly we realize that the algebra that comes out of this construction is something that we were looking for many, many years as a possible candidate for a higher-spin algebra, because it passes some very important admissibility conditions, which actually rule out most of other candidates. And the condition is pretty much like, if we want graviton, for example, not an ADS3, but say an ADS4, we know what is a module associated with graviton, we know the lowest energy, and we should check that if we have some algebra, then it admits modules where graviton actually may sit. It turns out that in most cases this does not happen. And for this algebra, it does happen. So that test goes on very, very smoothly. And another comment that I would like to make immediately is that it contains some ideals which are somewhat analogous to the rigid trajectories. So one can consider subsectors of the algebra and corresponding theory with larger and larger set of fields. The simplest one is just the kind of original higher-spin algebra, which is normally associated with the, so to say, first rigid trajectory in string theory. It's indeed very similar. So from many perspectives, it looks like this might be a very good proposal for testing how to formulate a theory. But so far, the open problem is how actually to formulate a nonlinear higher-spin string-like or this multi-particle symmetry-like theory in the bulk. I'm not talking at the boundary. I want to have a similar theory similar to higher-spin theories in the bulk, and then to see what will happen in ADS-CFT, for example, framework. So this is the proposal. Unfortunately, actually, I was going to talk mostly on this issue, but then the new news came, and I decided to focus also on the locality issues as well, because if there are claims that there are problems with locality, then there is not so much sense of looking for a corresponding multi-particle theory as well. So let's first discuss how this works in usual higher-spin theory, and once it works, we can go to further extensions. Okay, so I have finished with the first part. If there are any questions, it's probably a good point to ask. If not, let me then go to a little bit of formalism, how the higher-spin theory is organized in 4 dimensions. I remember that this workshop is on ADS3, and I will make comments on ADS3, but I would like to mostly discuss the 4-dimensional model because it's, in a certain sense, it's richer and more restrictive, so it's important to understand things from that perspective first. Then I will explain where the 3-dimensional models, how they are related. So in 4 dimensions, we have propagating gauge fields, and that's what makes difference compared to 3 dimensions where the gauge fields are Chern-Simons. So the first step is to introduce a right framework for description of gauge fields in terms of differential forms. This will allow us to control gauge symmetries and consistency of equations at the same shot. And this is achieved following by now standard methods that we introduce higher connections, which are all one forms but carry more and more indices. So for generic spin, the number of indices is related to spin by this formula, so that for spin equal 1, we have no indices. We don't have any space-time indices except for one form index for spin 1, and so on and so forth. So this is spin 2, and this is spin 3/2. For higher spins, it goes on, and the point is that there are more and more auxiliary fields like Lorentz connection and gravity that take part in the game, and they actually parameterize higher derivatives of the original fields. They pretty much like Lorentz field. Lorentz connection in gravity describes first derivatives of Firbein. Okay. And then as a next step, let me show you how one can reformulate free field equations for all massless fields in 4 dimensions in a very concise form I refer sometimes as the central on-shelf theorem because it's actually is a very important statement. The statement is that this equation have this form where curvatures somehow are related to the component C of 0 y bar and cy 0. And there are covariant constancy conditions on the field C. So the meaning of this is as follows. Most of the curvatures are 0, except for those that are either anti-holomorphic or holomorphic in Y. And these curvatures describe precisely the self-dual and anti-self-dual components of the Weil tensor, for example, in spin 2 and higher spin generalizations. So this is how the equations are organized. All equations, all curvatures are 0 except for Weil tensor and their higher spin analogs. And there are other equations that either express compatibility condition for this or just impose the equations on the matter fields very much the same way as I have discussed in the 2 + 1 dimensional case. So these equations are actually similar, and explicit formula are given here. So R is just a joint covariant derivative that has very simple form like this, and d naught tilde is twisted adjoint having this form. And what is important here is again that what we have seen already in the 2 + 1 dimensional case, that space-time derivative by this equation is related to d dy bar. So every second derivative in y is one space-time derivative in x. Let's remember that. Okay. The following comment is in order, is that in this language it's very easy to identify what is self-dual and anti-self-dual of higher spin theory, at least at the linearized level. And actually this is the case when one of these fields, holomorphic or anti-holomorphic, is 0, pretty much like in gravity. So those are left and right components of the generalized Weil tensor, or introducing the parameter eta that I have introduced in these linearized equations here and here. This is the case when one of them is 0. Okay? So if we consider a theory where one of these parameters is 0, we are actually considering an anti-self-dual theory, and that was conjectured even at the nonlinear level, which I will discuss in a moment. Okay. So how things are promoted to all higher order corrections to make it possible to extract higher order corrections and at the same time reproduce the free field equations in the form of central on-shelf theorem at the linearized level. Well, this is achieved by somewhat enlargement of the system by letting some more spinor variables be involved into the games called z variables. They are again spinors similar to y's. So we extend our 1 forms to w depending on z, and also we extend our 0 forms to b depending on z, y, and an additional what we call Klein operator just to allowing to make it automatic to go from a joint covariant derivative to twisted adjoint that should act on the field C. So, okay, in addition, it is convenient to introduce a connection that will describe evolution along the z variables. So with these preparations, the whole system takes this very simple form, actually. So the system that describes full nonlinear story about higher spin fields in 4 dimensions has this form where star product is given by this formula. It's actually a very standard formula that describes Weil algebra with respect to both z and y variables. So they commute with respect to this y and z like this. It's slightly different compared to usual Mayel star. It's actually normal order. It's star product, but nothing more complicated than that. There are some operators which are called inner Klein operators that flip chirality and that explicitly appear in these equations. However, even though they explicitly appear, they don't spoil the formal compatibility of these equations, and that's actually his whole story. All right. So what I would like to emphasize is that, again, setting one of these numbers to 0 was conjectured in 92 to correspond to the self-dual version of higher-spin theory, and we will come back to this story. So that is how the full system of nonlinear equations looks like. It can be actually written down in 2 lines, but then it would take a little bit more time to explain the meaning of the letters there. So, in fact, it is, I think it's really very simple, but unusual. That's why sometimes people get confused when looking at this. So one should then, to make sense of this system, one should analyze it perturbatively somehow. And to analyze it perturbatively, one should find some vacuum solution to this full nonlinear system of equations. And actually, there is a very simple way to do this. Just setting 0 form to 0, then S naught can be taken in this form linear in Z, and then the remaining equation on W that only remains to solve is a flatness condition that can immediately be solved in this form with some connection by linear in Y, and connection then describes just the background ADS space. This is how ADS space appears in this setup in a very natural fashion. So this is where ADS4 comes in. Okay, so then one can analyze perturbatively corrections, and in the lowest order one finds that the 0 form first order contribution is precisely the Y-independent field, which was already, we have seen at the linearized level. We can find correction to S, we can find corrections to W. Again, it will start with some field that was called omega in the previous analysis. That was the higher spin gauge fields, plus some C-dependent corrections. Okay, and then one can analyze the system order by order in principle by noticing that commutator to S naught is nothing else as the RAM differential with respect to Z spinors. So this is dz ddz. Basically, what happens next is that one solves at any given order, plug the resulting expression to the right-hand side, and arrives at the equation that dz of some new unknown is expressed in terms of the combination of the already known combinations of higher spin fields. And this should be solved somehow. There is a standard way how one can solve this. Okay, so that's is by usual homotopy trick. However, one should remember that there is a freedom in this case, so one can define the simplest that I would call Poincare homotopy operator, and this operator is defined up to a closed form which contains both non-trivial homology and exact forms. So basically one can go order by order, but here one should choose appropriate homotopy operators which is compatible with locality. This is very important issue I'm about to come to. So what one can do, one can then analyze order by order corrections, and the first non-trivial corrections will just correspond to the corrections to equations due to currents. Formally it will look like this. There appear some additional terms by linear in C called J here as well as here, and J should obey the current conservation condition. If one would compute the result, then one will get some corrections, but before analyzing these corrections, let me make a brief comment on what is local, what is non-local in this setup. This is very important. Well, number one, the comment is that in ADS, it is actually a non-trivial issue because expanding in powers of derivatives is not necessarily a well-defined object, because commutator of background derivative in ADS is of order 1. It's because dimensionless combination is just curvature divided over this lambda, which is just 1. So when one expands like that, then actually there is no room for a low energy expansion at all, like in string theory. And the issue is about the properties of these coefficients in ADS. That makes, so this is how one should analyze the problem by trying to find appropriate restrictions on the coefficients A. And that makes a lot of difference compared to Minkowski space, because one can play with different convergence property of these coefficients, while in Minkowski for massless fields, the best one can do, one can write down something like 1 over box for a non-local expression. Here there is plenty of options in between. In terms of spinors, what is local and what is non-local actually is even easier to understand, remembering that dy is x derivative. And that actually tells us immediately that if we have some expressions containing infinitely many contractions between y here and y here, and at the same time y bar and y bar here, this is going to be non-local because it will contain infinite power series expansion in x variables. However, if we manage to arrange our corrections in such a way that the number of contractions will be finite with respect to either barred or unbarred variables, then it turns out that these terms are just local in the standard sense, which means that for any given 3 spins, those 2 constituent spins of the current and the third spin of the current, then actually the expression is precisely local. It just contains a finite number of derivatives associated to these 3 spins. So this is the game that one should play when analyzing what is local, what is non-local in the higher-spin theory in these terms. And I will very briefly, because of lack of time, I will skip all details, but basically what happens is that one can first derive corrections from standard homotopy operator, and they become non-local because there are contractions between s, t, s bar, t bar, due to this integral. And then one can find a better homotopy operator such that which is related to the original one by adding a term in the homology, but one may or may not refer to this relation at all, and the final result turns out to be local because, for example, in this term there is no excuse me, this is the filter definition, and this is the resulting current where there are no contraction between undotted indices, for example, here, and there is a conjugated term. So by this, one obtains the explicitly local expression on the right-hand side, and this is actually the proper result. So because of lack of time, I'll probably skip details of how one proceeds similarly in the one-form sector. This is the work that have been finished essentially here with Olga Gelfond. And again, one just redefines the homology, the homotopy operators, and the final result also turns out to be local. However, here is a subtlety that one starts with expression derived from nonlinear field equation that depends on eta squared and eta bar squared, while eta bar contribution is identically 0. But when one applies these new homotopy operators, what one gets is just opposite. It turns out that all eta squared and eta bar squared contributions disappear, and one is left with local current interactions proportional to eta bar. That is somehow unexpected, and when people were trying to analyze the story just in the sector of eta squared, they were not able to find the proper local expression at all. Okay, so that was the technical part where I wanted to, illustrate several issues here. One issue is that this is not so much difficult to derive the expressions and to derive the local result. And, actually the results were presented here. I'm not discussing the issue why these results are the only possible ones, but actually this is true. I mean, this is the only way how one can consistently go to the local current interactions in 2+1 dimensions. So let me just summarize first. And first I would like to emphasize that there is a uniquely defined current interaction in this system which is absolutely local at the level of first order corrections. There are no higher derivatives. Well, there are higher derivatives, but any time for any given 3 spins, only a finite number of them. All right. So important issue, how to extend this to higher orders. This is work in progress. And from that perspective, it might be interesting to look at some earlier paper by these authors, two of whom I guess are here around. And also let me give you a quotation from a very recent paper by Slate and Tarona, where they state that in 3 and 4 dimensions, the G, S1, S2, S3 coupling constants, which are just the current coupling constants in the current interactions, were extracted from the unfolded form equations referring to these papers and were shown to be divergent. When I read this, I was a little bit surprised. I've checked my own formula. There is no divergences there. So I'm not sure whether collaborators of Tarona do agree with this statement. But anyway, there is a apparent or clear, whether to say, discrepancy with what I was just explaining during this talk. There are no divergences. There are uniquely defined current interactions. On the other hand, this is I've taken from this paper of Slide and Tarona directly. It looks like, well, it's a kind of parallel word. And in more modern terminology, it looks like this is just an alternative fact, let's say. Okay. So I'm referring to this because they actually put forward another interesting statement on locality in the higherspin theory, which I will briefly comment in the next transparency before going to conclusions. So they put a no-go statement on the quartic interactions in the higherspin theories, saying that they are badly non-local. What can I say here is the following, is that I disagree again with what they actually try to say. I heard from some people there is a rumor that actually the paper contains just wrong coefficients. If they would be corrected, then actually the situation will be different. But independently of that, what I can see is that based on some conjecture on the behavior of summation over infinite sets of intermediate spins in this theory, they arrive to this conclusion, which has little chance to be realized in any bulk higherspin theory, because we actually do know how the quartic vertices will be organized in general terms. And in this setup, it is clear that it is practically impossible to distinguish between what they call current exchanges, those that are involving the inverse D'Alembertians with some masses, and what they call contact terms, though they are not involving the such operators, but just contract derivatives of different spins. So one can actually see that this current exchange contribution will be of measure 0 in this language using the formalism that I have introduced. Is fairly clear to see, and actually I don't think this fits the conclusion of this paper. Well, another comment is that it's not quite clear why actually the authors did not check their conjecture by using the known form of the higherspin algebra. Okay, I wanted to say a couple of words about the boundary limit related to what Jenny was talking about. I will probably mention that two facts and then come to the last slide, to conclusions. The point is that one observation that was made in this paper of the last year, where the current interactions were derived in the zero form sector, is that it automatically reproduces the dependence on the phase parameter that was predicted by Zhiboyedov, Maldacena, and Giambiin when analyzing NDS-CFT. So the phi dependence just comes out right precisely in the right way. That I don't think that Jenny has mentioned in his talk. And actually that's why these results were anticipated to reproduce holographic duality in the right way. And let me come to conclusions now. So the conclusions are that if one would really apply proper homotopy operators in higher spin theory, then everything is okay with nonlinear higher spin equations. The confusing statements in the literature just disappear. But one should be able to find appropriate homotopy operator. That is some tricky game that I have not explained here, but it will be explained in some subsequent paper. Another comment is that, surprisingly, even though the final result for current interactions depends on eta bar, it on the one hand side it reproduces duality, what is expected from holographic duality. On the other hand side, is perfectly consistent with the conjecture that the cases when eta equals 0 or eta bar equals 0 correspond to self-dual higher spin theory, and actually just proves at the second order that the original conjecture was the right one. Let me emphasize that what is interesting from this general perspective, that formally the four-dimensional self-dual higher spin theory is the same as the three-dimensional higher spin theory, up to a different choice of the vacuum state. So one should start from a different vacuum, take four-dimensional self-dual higher spin theory. It will be equivalent to the three-dimensional higher spin theory, as I said, up to the choice of the vacuum. And the issue of the phase dependence is resolved in this setup in a natural way. So there are many directions to work on. And as I have mentioned already in the previous talks, well, the most urgent one is to compute three-point functions, and that's what we were doing with Slava Didenko. And I was very much surprised to hear yesterday from Zhenya that they are also working on this with Sezgin and someone else. Because relatively recently he was trying to convince Didenko that one should never do this. Okay, so many other things should be done. Probably I should stop here. They are written here. Okay, thank you.
More of a comment, but often to clarify what is local and what is non-local, one would need to know how a field interacts with other fields, or even better with an external source, because it's very easy to create a non-locality if you choose the wrong source, which is, say, 1 over box times the right one. So I suppose this essentially means that I don't know how you would progress in this case, because here you are not so free to add external sources to
I don't really know how to add external sources. This is very difficult here because they should obey compatibility conditions. Due to compatibility, and this will be field-dependent conditions. I simply don't know how to proceed this way. But I think I know how to define a proper class in terms of the fields involved into the game. So by restricting these types of contractions that I was referring to, I'm not sure, I mean, it goes a little bit, it's a little bit more technical than what I have presented, but it looks like that there is a simple criterion that there is. I mean, this particular choice of the homotopy operator that I was advertising is very, very special, just from the perspective of how many contractions in the how many space-time derivatives, if you like, in different languages appear. Okay, I don't know if this is enough or not.
Do you see a direct link between the candidate stringy higher spin algebra that you uncovered and then the one that was discussed by Gabriel Gopakumar for strings on ADS3?
Okay. I don't see a direct link, but I think I know where to go to try to check the relation. Actually, these two constructions do converge somehow, because there is the universal enveloping structure in the algebra of W algebra, and here is the universal enveloping algebra of the say, three-dimensional higher-spin algebra, which asymptotically should talk to each other. I mean, because during this Brown and Noah formalism, this does not mean that I immediately claim that they are the same. But what one should do, one should, there are plenty of possibilities actually here. One can try different algebras. I mean, starting from four-dimensional case is different than starting from three-dimensional case. I think there should be a parent algebra that would unify all of those. And to go to particular algebras analogous to those that Matthias was considering, I would propose to start with a more symmetric case, which would sound like higher dimensional case from that perspective, and then to think which, number one, how to break symmetries. In this setup, there is a good chance to break symmetries because there are fields that can be used as Higgs-type fields for higher-spin fields, up to something smaller. So this something smaller should probably correspond to those algebras that Matthias and collaborators see from the boundary side. But of course, saying this is just the beginning of the long-scale project. I mean.
Any other question? Otherwise, thanks, Misha, again. Before we leave, there is an announcement.
Yeah, a quick announcement.